All right, now that we've had a tour of the airflow demonstration unit, I'd like to go over the data sheet quickly, or not so quickly. It's important for you all to know that we are going to email to you a filled-in data sheet. So it's going to have all the data already on it. As we film later videos with actual data recording, you'll see me write figures down on a data sheet, and I'll hold that up to the camera. I don't want you to try to record those at all. You're going to already have all of the data, so don't worry about that. In those videos, I'm just showing you how we are filling in the data sheet from the manometers. So here's the first page of the data sheet, and this talks about the procedures. Again, there are 5 separate exercises that we will perform, as we briefly talked about when we did the tour of the wind tunnel. We have the 48-point pitot tube traverse. We have the P equals RQ squared investigation with the flow regulators. We have the shock loss with the flow regulators. Then we have the expansion contraction duct. And then finally, we look at the effect of évasés on airway performance. I'm going to skip pages 2 and 3 for the time being. Those concern the analysis of the data. And I'd like to show you the data collection sheets themselves first. Here is the data collection sheet for the first exercise, and this is the 48-point pitot tube traverse. Okay, so you see here a grid. It's numbered from 1 to 8 across and A to H vertically. So those correspond to markings that are on the side of the wind tunnel. And there's a bunch of X's in a lot of these boxes. We don't need to record data in those boxes, just in the blanks. So in the video, we'll probably record point A2 and A4 just to show you what we're doing. And again, the pitot tube is connected to the manometer to measure just the velocity pressure in inches of water column or inches of water gauge. So pretty straightforward there. And just a note on the spacings, if you look at the video closely, you'll see that the spacings aren't uniform. It's kind of like when we did the traverse of the bag line a few weeks back. And if you remember, we traced concentric circles of equal area. And that's also going on with these rectangular segments here. So they aren't uniformly spaced on the outside of the airway. Then down below that, we have a space for a centerline velocity pressure reading. And then we tilt the pitot tube off axis by 10 degrees, 20 degrees, and 30 degrees. And we're just looking at the effect of being off axis misalignment. How much of a problem does that cause with the data? Now, the important thing is the centerline velocity reading. All exercises after this, we're going to take only centerline velocity pressure readings at this same station, but we're going to use this data to figure out what the average velocity is, and we'll develop a correction factor. You will develop a correction factor to multiply the velocity that you calculate from the centerline velocity pressure and end up with the average. And then also here we've got the barometric pressure, inches of mercury, wet bulb and dry bulb temperature. You'll use those, as you have many times already, to compute the air density. And from there you can compute the air velocity from the velocity pressure. All right, the second exercise, we are at the flow regulator station now. This is the plexiglass frame where we insert the panels with different cutouts. So we're measuring the centerline velocity pressure at the same point we did the last exercise. And then we're measuring delta static pressure between 2 taps that are downstream from this flow regulator station. So we're looking at the behavior. We're just using the flow regulator station in this exercise to control the flow, to reduce it. And we're looking at the velocity pressure and then the delta static pressure. And this is for us to examine the relationship of P equals RQ squared. For this, you'll need the duct to calculate Q, and you're going to need Q for lots of the other exercises. So just remember, it's 5 inches tall by 4.5 inches wide, and of course, you want to convert that to square feet to get CFM for Q. The third exercise is at the same test section, the flow regulator section, and we're doing almost the same thing, except that delta static P is now measured across the obstructions that we're placing into the plexiglass frame. So again, we're writing down the regulator sizes. In this case, when we do the analysis for this exercise, we're going to need these areas. The previous exercise, we didn't need the areas. We just needed those to keep track of where we were. So again, we record the centerline velocity pressure and then delta static pressure across the obstructions that we're placing in the flow, and this is directly related to shock loss. And we'll talk much more about this when we take the data and then when we analyze it. The fourth exercise is that we are looking at shock loss across the plexiglass contraction expansion section. And for this one, you remember seeing the video of that. We have a test section that we swap out, and we're just looking at the change in static pressure from upstream to downstream of the whole assembly. So this one goes very quickly. We have two orientations for it. We look at the overall delta pressure and the velocity pressure. So in the first orientation, we have a gradual contraction into the constant area smaller duct and then an abrupt expansion. The second orientation, an abrupt contraction to the smaller size duct and then a gradual expansion to the original size duct. And for this analysis, you're going to need the area of the small duct, and that's recorded here, and there's the main duct again. Our final exercise is we're just going to swap out the évasés, as I talked about, and we're going to look at how the velocity pressure changes and also the delta total pressure at the discharge, okay? Very quick exercise for that also. We have cases of no évasé, short, medium, and long ones. Goes very quickly, and we'll talk more about that when we do the exercise. Okay, now I just want to show you the last 2 pages of the main lab handout. Let's see here. We have some copied figures that are from different textbooks, and these are going to be used in the shock loss analyses. We'll make a separate video of those. There's quite a bit. It's not rocket science, but there's a lot of different things to do, and there's some very small nomenclatures. So we're going to have to make another video or possibly a very extensive handout about those, just so you know why these are included on the handout. And then the last page of the handout has some additional formulas that you'll need for the shock loss calculations. Okay, up here, so, and some coefficients for those. And then at the bottom, I just wanted to show you some of these figures from some fairly old books, published work, but they're pretty well done because they kind of show what happens in some of these shock loss examples. So here we have a sudden contraction from an original area to a smaller, and you can see from these streamlines, that's what the arrows are, so those represent the actual motion of particles. Some of the air travels in the wrong direction, and it takes extra energy to get it going in the proper direction. Same thing going around a corner. You see vortices here and vortices here, and some of this we saw during our second lab session when we did the anemometer traverse of the LME hallway. Okay, next sheet here is some of the equations that you'll need. Hopefully this is all of them. Many of these you have seen already. So air density, W is 70.7 times the barometric pressure divided by the gas constant times the absolute temperature. The data sheet that you will get will have the barometric pressure and the room temperature. So remember to add 460 to that. For T, you can figure out the air density. It's usually about 0.065 pounds per cubic foot. Then using that and the velocity pressure V sub P that you will record from the pitot tube, you can get the air velocity. So feet per minute, inches of water gauge from the manometer, and again the air density that you calculated up here. Quantity, Q equals A times V average. A is the cross-sectional area of the airway. So for the most part, that's going to be 5 inches by 4.5 inches converted to square feet. However, for the shock loss calculations, you'll need to calculate the dimensions of the openings, which will also be in square feet. And then V sub av, AVG is the average air velocity. So you're going to get this from for the most part, from the centerline velocity pressure. You'll convert that to a centerline velocity, multiply it by the correction factor from the first lab exercise, and you'll get the average velocity. Airway resistance, R equals P over Q squared, which comes from P equals R over Q squared. So units there are just based on whatever P and Q you use. In this case, I wrote this equation here because we're looking at R and we're looking to see if it's a constant. Okay, it's supposed to be a constant. It might not be in your analysis, so maybe you can speculate on some reasons why. Then the shock loss factor, which is X, is defined as delta P divided by velocity pressure. So X is a shock loss factor, it's dimensionless. Both of these pressures are in inches of water column or whatever. They could be pascals, whatever. X is going to be dimensionless. Basically, the larger the X, the worse your shock loss is. And we'll talk more about that when we do the separate video for analyzing the two main shock loss experiments. Okay, I think it's time to start taking some data. And we'll see you at the 48-point pitot tube traverse test section.